Hey everybody, this is the lecture on 8.3, Applications to Physics and Engineering, and specifically what we're going to be talking about in this section is moments and centers of mass, and then eventually, I should say, centroids, and we'll talk about what those are as well. Before we get started, we're going to do some derivation, some basic stuff. The first thing that we're going to talk about is the old seesaw or teeter-totter. Depending upon where you're from geologically, you might call it something different, right? But we're talking about balance. And so what I have here is this horizontal bar, right? And on one side we have a large mass, and on the other side we have a small mass. And the way that we can balance that exactly is if we have the fulcrum or balance point a bit closer to the large mass than it is to the smaller mass. And the physics that governs that balancing is that mass 1 times distance 1 has to be equivalent to mass 2 times distance 2. Since mass 2 is so much bigger, we have to have that distance 1 is larger to counterbalance that. Now, what we need to do is we want to find this center of mass, so to speak, this balancing point. And we're going to do that by basically using the following. Now, what I want to say here is this idea of mass over a distance, or mass times a displacement. This is the moment of the object. So when we talk about something's moment, we're talking about a mass times a distance, and that's going to be important for us in our calculations a little bit later. So make sure that you key in on that idea. A moment is a mass times a distance. So what we're going to do in order to find the location of this balance point horizontally, which we're going to call x bar, the center of mass here, we're going to put this in the context of a number line. So what I've done is I've brought these same masses down and created them as point masses here. Mass 2 is located at x2, mass 1 is located at x1, and I have my balance point in the middle, x bar. And so we're going to introduce some math here. Now, instead of calling this distance 2 and distance 1, we can impose some mathematics on here. Distance 1 is equal to x bar minus x1. That's right minus left. Whereas distance 2 is equal to x2 minus x bar. And what we see here is we can rewrite this as mass 1 times x bar minus x1 is equal to mass 2 times x2 minus x bar. Now our goal is to find that fulcrum point, x bar, and so we're going to solve for it using some simple algebra. So if we multiply this out, this is mass 1 times x bar minus mass 1 x1 is equal to m2 times x2 minus m2 times x bar. And we're going to collect all of our x bars on one side. This is mass 1 x bar plus mass 2 x bar is equal to m1 x1 plus m2 x2. And if we factor out an x bar, we get m1 plus m2 is equal to m1 x1 plus m2 x2. And if we solve that for x bar, we see that x bar is m1 x1 plus m2 x2 over m1 plus m2. And in fact, I should say, if we had multiple masses here all over the place, we could extend this even further, and it would be a simple example of us extending that as plus mass 3 position 3 or distance 3 plus mass 4 distance 4 plus dot 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 over mass 3 plus mass 4 plus dot dot dot, should we need to include more masses here. But we're not really interested in solving for x bar at this point. What we just want to notice here is, conceptually, the denominator here is the sum of the masses. And the numerator, maybe I should write that a different way. The sum of the individual masses sub I, where the numerator is the sum of MIXI. So conceptually speaking, what we're talking about, let me move this over here. Conceptually speaking, what we're talking about here is X bar is the sum of what? Well, let's take a look at this. This is a mass times a distance or displacement or location. Either way, this is the sum of the moments over the sum of the masses. Okay. So that's a pretty straightforward example, or derivation at any rate. So let's highlight that. That's an important concept for us. So why wouldn't it be true in the y direction as well? In fact, why couldn't we go ahead and find the center of mass in a two-dimensional problem? So what are we talking about here? So down here in this next little diagram, I have three masses, mass 1 at x1, y1, mass 2 at x2, y2, and mass 3 at x3, y3. And what I want to do is I want to find their centroid, or their center of mass. We're not talking about centroids yet. And the way that you can think about this, in this particular case, is think about each one of those masses as being a ball. I'm going to try to draw this with some perspective. And what we're talking about here is each one of these ball masses on the end, mass 1, mass 2, mass 3, and think about a really thin plate that connects those guys. And what we're going to try to find, is the point in the middle here somewhere. Where is this? What we're going to call X bar, Y bar, such that if you were to balance this plate, it would be balancing perfect, right? So this is the fulcrum or balance point, or in our case, the center of mass. That's what we want to try to find here. So let's see if I just connect these dots. I would expect it to be somewhere on the interior here. And let's go ahead and talk about how to calculate this directly. Let's see. Let's go ahead and give these masses some values. Let's let mass 1 equal, let's see, let's just use some unitless stuff here. 2, mass 2 equal 4, and mass 3 equal 1. And we'll go ahead and use the coordinates I've kind of got laid out here. Let's call this 3, -1, and this will be -3, -2, and it looks like this is 1, 4. So let's see if we can't use this formula to sort of eyeball where we think the center of mass in this region is. Where's the balancing point? Okay, so let's see. Apparently, X bar is the sum of the moments divided by the sum of the masses. Now in this case, let's see, the sum of the masses should be pretty straightforward. That's just going to be 2 plus 4 plus 1. As far as the sum of the moments go, that's going to be mass 1 times distance 1 plus mass 2 times distance 2 plus mass 3 times distance 3. Now, since these are x values, we're going to be calculating those distances relative to 0, right? This is 1 unit horizontally for M2. This is, let's see, or position, I should say. X value is 1. Here, the sign is important. This is x equals -3 for mass 1. And +3 for mass 3. And, oops, don't peek at that. What we get here is -6 plus 4 plus 3 all over 7, which is 1/7. Is that right? No. -2 plus 3, yeah, 1/7. So that's our x bar. For y bar, the formula is actually the same. It's the sum of the moments divided by the sum of the masses. But unlike the moments that we had up here, which were the sum of the mass times the x distance, this is now in the y direction. So let's get a different color here. Let's see. Red. No, I already used red. Dark blue. So our first y value is -2. Our second y value is 4. And our third y value is -1, as indicated by those y values, location-wise. And so, again, what we have here is the mass times the position, a y1, which is -2, plus the second mass, 4, times the second position, which is 4, plus the third mass times the third position, all over the sum of the masses, which is still 2 plus 4 plus 1. And this time we get -4 plus 16 minus 1 over 7, which is 11/7, and that's y bar. So if we go back to our picture here, 1 over 7 is, well, pretty dang close to 0, 1/7. So I'm just going to put in something really close there. Oh, not on top of the axis here. Come on, move. Okay, that's about as close as I can get without it snapping to. So let's call that x bar. Y bar is 11/7. That's a little bit bigger than 1, right? That's 11 4/7. That's almost 1.5. It's a little bit more than 1.5. Y bar at 11/7, x bar 1/7, and that is my center of mass. And it's heavily skewed to one side, but that's because mass 3 is so much lighter than mass 2 and mass 1. So you'll notice that that red dot in the center is quite a bit closer to mass 1, mass 2, or that left side of the triangle, than it is to the lower right side where mass 1 is at, because if we're going to balance it, it's going to need to be closer to those heavier sides. Otherwise, it'll tip. But then, yet again, it's still closer to mass 2 than it is to mass 1, because mass 2 is the heavier of the two masses, mass 1 and mass 2. So that looks reasonable as far as a balancing point goes.